Okay, welcome back. The demo I'm going to do now, I'm calling it work to lift the string. Okay, so I'm going to first take a string and lay a certain portion of it over a table. So then I'm just going to ask a question such as, okay, how much work does it take for me to take the edge of this string and then go and then lift it to the height of the table? So just basically take the edge, go all the way like this so that the string is sitting flat on the table. Then I'll ask a related question. Then I'll say, okay, what if the string is hanging from a certain point? How much work does it take to take a certain point along the string, take it, and then hold it from that same point? Okay, so that the end result will look something like this, or like that, and then this piece will be dangling from there. Okay, like that. So then how much work does it take to do that? So I'll do this case first, and then I'll show how to do that, and then I'll do this, and then you'll see that they're related. So basically it looks something like this. So imagine the string is hanging over like this, some portion of it over the edge, and so all I need to do is just take the string and then just lay it on the table. Okay, so that's all. Just take it, put it at the level of the table. Okay. Now for this portion it will look more like this. I can hold the string like this at the tip, right? And then I can take any point along the string, go like this, lift it, and then hold it from there. See? So you see how this piece is dangling? So how much work did I do now in lifting that portion? Okay, what if I lift the top? I go like this. Now how much work did I do? I didn't do a lot of work. That was easy. So the higher up I do, it doesn't require a lot of work. But down here requires more work. I have to lift it, you see? Lift it, hold it here. So that's harder. If the rope was really heavy, that would be really hard. Down here, go all the way up. And then a piece of it is dangling. Okay, so let's do the calculations. Let's do the one where it's just hanging over the side. I've already weighed my string. It's not too heavy. It's 15 grams. Okay. So it's 15 grams. And then assume I've already measured the length of it. All right. So the total mass of it is going to be 15 grams. Right. And let's say I've already measured the length. The length is 1 meter. So let's say 40 centimeters of it is hanging over the edge of the table. 40 centimeters. So how would I calculate that? Well, first there's an integral approach. I'm going to show you that. But then I'm going to show you, after the integral approach, a different way of looking at it. And I'm going to show you that it gives you the same result. The integral approach is to say, take a little piece of the string that's hanging, okay, and then it has a mass of dm, and then ask yourself, how much work does it take to lift that to the height of the table? So consider the distance from here to here, x. And then consider the distance from the table all the way to the bottom of the string, h. So that's how much of it is hanging over is h. And then x is the distance from the top of the table to a certain element along that string, right? So how much work does it take, dw? So it takes the mass of that little element, dm, times gravity, times the distance that you have to move it, which is x. So of course I'm assuming that when you're moving this up, you're doing it at constant speed. You're not accelerating it up. So the amount of work that you are exerting on it is equal to the same as its own weight. Its own weight is dm times g. So you're exerting just enough force to make it go up at constant speed. You're not accelerating it up, right? So then I'm going to define something known as linear mass density. Lambda is equal to dm over dx. Then I can say dm is equal to lambda dx. The linear mass density of the string times dx. So then I can put that in there. Lambda dx is dm, and then gx. So then I'm going to integrate this, and I'm going to get the total work necessary to lift that portion up. Well, lambda of the string I'm assuming is constant, so it comes out of the integral as m over L. Right? It's the ratio of the total mass of the string over the length. The lambda is m over L. And then the g is constant. That comes out. And then you have integral x dx from 0 to h. right? From all the way from 0 all the way to how much of it was hanging, right? So then when you integrate that, what do you get? M over LG, and then you're going to get x squared over 2, and then from 0 to h is just going to give you h squared over 2. Okay? So this is the result that you get when you do it the integral way. Okay? But now let me show you a little bit different way of looking at this, and it might enlighten it a little bit more. The other way we can say about approaching this is say, well, how much where is the center of mass of this shape, right? So where's the center of mass? Center of mass is here, right? So how much work does it take? Imagine all of the mass of this string which is hanging. I'm going to call that little m, because it's not equal to the total mass of the string. So imagine this portion of the string that's hanging has a mass little m, and imagine as if it's all concentrated at the center of mass, because that's the definition of a center of mass, is that you can imagine as if all of the mass is concentrated at its center of mass, right? So how much work would it take to lift that from here to all the way to here? Okay? So you could say the work necessary to lift little m is going to equal little mg times what? Well, the distance that you have to move it is h over 2, right? Because we're assuming it's uniform density, so it's going to be just h over 2. Okay? So you take the mass of the hanging portion of the string, and then you multiply it by half of the height that's hanging, right? So then I'm going to say, well, what's the mass of the hanging portion as related to the total mass of the string? How much does it weigh? Well, we're going to say the ratio of the mass of the string over how much of it is hanging, right, is equal to the ratio of the total mass of the string over the total length of the string, right? Little m over h equals big M over L. When something is a uniform density, its mass is the ratio of its length to the total length of the string times the total mass of the string. So then we can put that here is equal to big M. So of course, if I put h over there, I'm going to get h squared, right? The h here is going to multiply by the h there, right? You're going to get here h squared. And then on the bottom, I'm going to have an L, and then the 2 is there, right? So 2L. So you're going to get mgh squared over 2L. That's what we got by integration. Mgh squared over 2L. Well, this was an easier way of doing it because we kind of thought about it more globally. Where's the center of mass of the system? And how much work do I have to do to lift the center of mass, right? And it was kind of easier to look at it that way. But it's good to see that where the integral, how to do it with the integral way, but then it's easy, it's good to see an easier way to do that. So now let's actually calculate with these with numbers. So I didn't have to do a lot of work, almost 12 millijoules of work that I did in lifting that 40 centimeters up. Now, of course, if the rope weighed a lot, it's big, thick rope or chain, then it's gonna, the mass is gonna be a lot more, and it's gonna be a longer length, and it depends how much of it is hanging, right? Okay, now, how about the other case where I'm holding it and I'm taking a certain point? That one is a bit trickier. So now let's say I'm holding it like this. Okay, 1 meter. And then let's say I take the 60 centimeter mark, 0.6, and I hold it from there and then I go like that. Okay, so then it would be like this. So the 60 centimeter marks would be somewhere here. So it would be like this, go over here. And then see what happens, right? So then this part is going to be dangling like this, like that. Okay, so then what we could do is we've done actually work on both pieces of the string. We've taken this part of the string and we've lifted it up by a certain portion, and we've taken this portion of the string and lifted it up. So we've done two work, right? So let's add up the work that we've done on both of them, right? So we can say W total is equal to W prime plus W double prime. Okay, W prime is going to be the mass of this portion, M prime. So M prime times GH prime. H prime is the distance between the center of mass of the M prime, right? M prime is just this portion here, Where is its center of mass and where is its center of mass at the end, right? So where is the center of mass of that piece? And then take the difference of that. So what matters is how much did the center of mass go up by. Okay, then we take the mass of this portion of the string, m double prime, times g times h double prime. How much did the center of mass of this one go up by? So center of mass, and then the center of mass here, and then I'll do the other one in blue. The center of mass of this one, and the center of mass here. Okay, how much did that one go up by, right? So let's do one at a time. So what's going to be the m prime? M prime is going to be equal to the big M of the string times the ratio of the length, right? 0.6 in this case, right? 0.6. So it's going to be 0.6 over the total length of the string, which is 1. So this gives me m prime. It's the total mass of the string times the ratio of this length, 0.6, to the total length, times gravity. Okay, what's h prime? This is probably maybe the trickiest portion. So where's the center of mass of the 60 centimeter string, like this portion? So the center of mass would be at the 0.3, at the 30 centimeter mark, right? So then when this one is curved up like that, where is its center of mass, right? So when you take a 60 centimeter string and you go like this and you hold it, so imagine the whole thing is 60 centimeters, that means from the top to the bottom is 30 centimeters, right? And center of mass is going to be at 0.15, right? So it's going to be at the 15 centimeter mark, right? So the center of mass originally is at the 30 centimeter mark, and then over here it is at the 15 centimeter mark, half of 30. So the center of mass went up by how much? By 0.15. I raised the center of mass by the difference between 30 and 15 centimeters, which is 0.15. So that's going to be my h prime, 0.15. Okay? Then I'm going to multiply this by m double prime. M double prime is going to be the mass of the total string. How much is the length of this? 0.4, right? 40 centimeters. So 0.4 divided by the length of the string. So you see here it's 0.6 over 1. Here it's 0.4 over 1 times gravity. Okay, now what's happening to the center of mass? Where is the center of mass here? Well, it's between 0.60 centimeters and 1. So the center of mass is going to be at the 80 centimeter mark, right? So 80 centimeter mark, that's 0.8. Okay, now where's the center of mass? Well, I have a 40 centimeter string dangling from the top, right? From here to here is 40 centimeter. So the center of mass is going to be at the 20 centimeter mark, right? See, notice it's not the same as the center of mass of the other one, which was at the 15 centimeter mark, right? So it's kind of tricky. You got to say, this 40 centimeter piece is dangling up there. Its center of mass is half of 40, which is 0.2. So how much did the center of mass of that go up by? Well, it used to be at 0.8 and it went up to 0.2. So it increased, the center of mass increased by 0.6, right? From 80 centimeters to 20, that's 60 centimeters, which is 0.6. Okay, so we put that here. Okay, so then we can just put down, we can factor out the m and the g. And then I just have 0.6 times 0.15, which is going to be millijoules of work. The other one I was doing about 12 millijoules of work, right? So I'm doing about 4 times more work on this one. So it's quite a more challenging problem. But notice, if I tried this with the integration method, it'd be just too much work to set up. So that's why I first taught you how to do the integration. Then I showed how to approach it differently. Then we can do this to any kind of case without having to do integration, without having to do 2 integrals for this one. I think it's very easy to do it this way, but you just have to make sure you catch the center of mass correctly, and then write down the correct equation for the mass of that portion, okay? So you can see we did about 4 times more work doing it this way than the other one. With this, you see a good example of how to calculate the work, how to do an integration, but then also how to see it in a different way. Thank you very much.